Well, it's been a while since we've done a video on the magnetic AB system. What I've got here is a transmitter, the 50 watt dual transistor output stage, 400 to 470 megahertz coverage, channel selection by these number inputs on the front panel. It's got input, separate deviation inputs. It's conceptually very similar to the receiver. If we go over here, there's a very similar modulator board, which is also a synthesizer. There's the exact same frequency reference, there's the exact same mixer circuitry, the exact same Hughes HCTRO320A. And this one isn't broken, unlike the receiver, so I haven't had to replace it. Then this is a modulator input, which comes from this board here, which is the AF board, and I've done a fair amount of modifications to it. But anyway, getting back to here, there's a loop filter. I've changed that slightly to make it slower, which was necessary. And there's a pre-emphasis network on the bottom side of this board. This connects to separate varactor diodes inside the VCO. So whenever you try to modulate a very low frequency, the VCO will actually be trying to correct that, and you can actually get ringing at that frequency. Specifically in this case 50 Hertz was a big problem. But anyway, as with the receiver, the local oscillator generated here is doubled internally, then goes over to this board where it's doubled again. Then it goes through a helical filter. There's no driver circuit in this can. Then there's a filter. And I have to extend the coil on this can by just soldering a piece of tin remover strap, braid, to extend the coils inside to lower their operating frequency. Once through the filters, which of course eliminate all the low harmonics of this local oscillator and any second and third harmonics and so on. And it goes into this Motorola part here, which I don't think I can read the part number of on camera, but it's a roughly 12 watt exciter. So basically a big power amplifier, and something like this would typically be used in a mobile phone, directly connected to the antenna. In this case, it goes through this coax here and then into a very exciting box that I might remove later, which contains two transistors and a quadrature coupler. It's two separate output stages that are then summed together and come out on this side. The reason I don't keep this thing open is because, one, there's fairly high voltages in there and it's outputting high RF currents because it's tightly tuned circuits, and second, there's a lot of beryllium in there, which is extremely cancerous, toxic to humans. It's also a damn good thermal insulator or conductor or something, I'm told. Anyway, the RF output goes out through this piece of nice coax into a low-pass filter, which also has a set of diode rectifiers connected to couplers. So you get forward and return power out through those two diodes. It goes out through a connector, I'm not sure what type that is. Interesting to note that the shielding here is connected to the chassis at these points. The insulation is actually removed here. This is of course, the output signal, and this line here is a coupled line which is used for testing. That goes out to BNC connector for a signal which is labeled -20 dBm, presumably a test signal. And then this is an N connector that goes out to the antenna, or in this case a bespoke RG405 cable with the requisite looping action to ensure that no electrons fall out of the cable in the sharp turns. This goes into a 60 watt dummy load I got on eBay, which actually seems to be doing the job quite well. There's no return power on a key up, as far as I can tell. Nothing that I can detect. So yeah, that's a really quick run through of this board here. There is some interesting stuff over here. This is a linear voltage regulator over here, which provides very nice power for the VCO and sensitive areas of the transmitter, separate from the raw 12 volt or 14 volt input on this connector here. It's about, yeah, as I mentioned, 10 volts. Here there's a 5 volt regulator, which I added, basically a mistake to add that because it's not really used for anything. There's a differential line input which is connected through this oscilloscope probe. It goes to an LT1990, two balanced 50 ohm lines technically, and that generates the single-ended AF signal in this board here, which means you don't need a nice ground connection between this and the receiver. That goes out on cable there, twisted pair over to the wiring loom here, and then through the front panel to this deviation adjust pin, and then into the VCO to modulate. So that's all good. That actually works really nice. The second op amp here is just a standard CMOS rail-to-rail, somewhat precise but not really op amp. This is an integrator that controls the power levels based on these 3 trimmer pots. You can set the upper and lower range for the power output. It's set in the volts coming out of this port here, which I'm measuring, and then you can control it from the front panel by this spare connector here, a trim pot. The third pot here is a return limit signal. So there's one integrator here which controls the power supply for this exciter module through these nice PNP power transistors. That modulates the power supply for the first stage of the exciter module, which is intended as a gain control input. You can use that to then set the output power through the entire chain by simply looking at the output power which comes in here, and then the set power, and then you simply trim everything in, and it all works quite nicely. It worked on the first attempt basically. The second transistor here is the second side of this the second side of the op amp, which is another integrator which looks at return power. When that starts to exceed the return power set, which comes from over here, of course, and that's just set with a trim pot here. Same unit as this one. It's basically unitless, but it's just a measure of how much you get. When that starts to exceed, it'll then steal the base drive from this transistor through this one, and that'll essentially override the signal from this one. So this will be trying to drive a certain power level. And then if there's too much SWR, return power, then the second integrator here will limit this integrator's ability to turn on the supply, keeping the amplifier inside a safe operating area. Although I don't actually know what the safe operating area is for this amplifier, but I've just chosen a somewhat low figure, and I'm just using that. I still haven't figured out what these cans are on this AF board here, but what I do know is that this is actually about 8 op amps, which involves several very sharp filters to process the AF signal, which is both the data and the voice signal, into a modulating signal which goes out over this coax on this connector here. And I've just disabled all of that. It's completely pointless for what I'm doing. It has tremendous phase shift across frequencies, very sharp filters. It doesn't work at all.
7:30 p.m.
So, yeah. Here's the receiver board. This is the synthesizer controller board and the loop filter, which has been rebuilt after I broke the old synthesizer controller. So this is a microcontroller, this is a phase comparator with SPI interface, this is a loop filter. It works basically on the same principles. It controls this VCO that's in here using a reference signal generated from over here. Very simple slot-in interface. or compatibility. Uses an analog sensing here, basically an R2R DAC, but a slightly special case to sense the position of this input on the front here. I haven't done anything with this board. I've got the same linear regulator here, and this switching module I plan to get rid of because it doesn't work. There's a line driver on this board which connects over to the transmitter for the TX signal. There's a modulator, discriminator tap here that goes essentially straight through. I tried to make a filter, but it's over here. It didn't really work. It gave me a lot of bit errors. I must have set the frequencies wrong, but the discriminator signal goes to this DVR-PTR V2 board, which has an Ethernet interface to the internet and the repeater controller software. So this is a very simple board. There's no gain through the differential driver. It's just straight up buffer. No, actually there is a gain of 2, just to provide more swing into the modulators. So this part actually works quite nicely. I spent a lot of time tuning up this loop filter with these 2 trim pots. Let's get the microphone cord out of the way. Yeah, there's not much to say really about this. It took a lot of time to do, but now that it works, it just sort of works. And yeah, ICSP header here, uncommitted, SMA port there, a LED that just blinks every time it samples the front panel settings, which is just lit up because I set up the clock speed to be pretty fast on this. It essentially just worked on the first try, getting this micro to run. A lot of time was spent trying to fix a bad power supply, specifically this bad power supply. So I replaced it with this one, and suddenly all my noise problems just vanished. And I've done a bit of tuning, just looking at the waveform that this generates when you change channel. You want it to sort of go up in a sort of nice damped response. You don't want it going up and, you know, oscillating wildly out of control whenever you change channels, because it's a regulation, it's a feedback system, so it has to be stable. I've actually got a bit of a problem over here. I need to slow down the modulator frequency response to avoid it actually canceling the low frequency components of the D-star bit stream. But I can't get that to work without making this VCO system very unstable. So I've sort of set it at a compromise where it gives acceptable performance at least. So yeah, did a bit of tuning on these filters just by setting a constant power output and then checking how much gain control voltage was applied. You could see how much gain was getting indirectly, how much gain this was contributing. A negative gain, of course. I've done a bit of trimming on this Toyocom 4 MHz reference. It's now within about 1 ppm at all times. There's not too much to say on this board. This all essentially worked. I tried to use some nice power detector ICs, but I ended up breaking them. So I decided that the easiest thing to do was to just use the diode detectors. For power, I'm currently using a Corsair CX430. I just got a moving box to keep it in. It's very quiet, 430 watts. Just got it today. What I found is that the voltage drop to the transmitter is too high. It's about half a volt, and that limits the output power as well. It pulls about 6 amps currently, but it's not reaching the full output power that I know it can do if it had maybe a few more volts of supply. So what I'm going to do, I've just twisted 1.5 square millimeter copper over, and it's a single pair. So I'm probably just going to run 2 more pairs, because there's 3 pins on the connector in the back plane there. When I do that, everything should work much nicer, but I know there's also a bit of voltage drop in the cabling inside the system, so it's not really optimal. Oh yeah, this power supply here is a modular type. If you can see it, I probably can't, but it's modular, and then I can disconnect each radio from the system without actually needing to desolder or make my own special connectors to handle high current. My plan for interfacing the transmitter and receiver is actually to get a second one of these and then put that in here, because I'm not using this DC jack and I don't need a power connector either, or a power button on the back anymore. So I'm going to put in a second one of these. That's in focus, and I'm going to do the same over here. I've already drilled some holes in the back there. That was a mistake. I was going to use 3.5mm stereo jacks to run isolated PTT and AF signals. Turns out my audio jacks weren't long enough to go through this thick aluminium chassis. So yeah, I'm gonna get rid of this board here. It's the old APC circuitry that's no longer needed. The only reason I keep it around is because it lets me light up this LED on the front panel when I push the manual key button. Let me see here. It's probably gonna cause havoc with the sound, but there, see? And that's actually a calibrated AF level. Not calibrated, but a controlled output level. Nominally, this thing doesn't actually have a good way of setting the power levels on the outputs. Let's see, here we go. Oh yeah, one last thing. I forgot to show you the inside of this PA. You can see it's basically made up of 2 separate boards, and I'm not going to poke a metal screwdriver at the beryllium chassis thinking about it. So yeah, I don't know what this transistor is, but I'm sure it's big and beefy and manly and beryllium based. There's power input, there's coupling caps, so feed-through capacitors they're called, between here and here. And this is the inside of the shielded box. These are meant to prevent RF traveling along cables by shorting them to the chassis. On the input here, there's a coupler just to read the power output. I'm not sure what that's used for precisely, but this is a quadrature coupler, which essentially has 2 outputs with half the signal, and one is 90 degrees offset, hence the name quadrature. There's a little resistor there which essentially takes any power that's fed in here and then reflected back. That ends up in this resistor over here. It's a very peculiar design with a big flat pad on the bottom, which seems to be bonded to the aluminium somehow. Very good thermal conductivity and probably very good inductance as well. So there's only 2 trimmers for these, and this stage is always on. It's a Class C amplifier with a tuned output stage. So it's presumably quite efficient. Doesn't seem to get very warm, even running at the full power I can get with 12 volts inputs. So these 2 trimmers essentially control both the input matching and presumably the phase as well, since if these are out of phase, then you'll have a problem at the output, which is another higher power quadrature coupler. There's a bigger resistor here, which is labeled as a 50-watt one, and that can that handles any imbalance to the output, or imbalance to whatever between the 2 transistors probably. So yeah, tuning this is actually fairly straightforward. You just look at the power taps. These are this output here is connected through a sense resistor to this one, so you can see how much current each amplifier draws. And you can tune by that as a first approximation. Then afterwards, if you're smart enough, you can look at this forward power tap, and then just tune for maximum output. And if you really want to get into the details, you can actually go over here and then take a look at this gain control voltage here, and then tune that for lowest gain control at a given output level. Actually using the integrators you can actually get linear control over this thing. I'm not sure how well it would do transmitting AM, but I might try that sometime. But essentially this integrator here is fairly fast. You could probably transmit a few kilohertz through it. And that seems to be able to control the output power from this amplifier even down to very low levels, probably over about a factor of 20 dBs or 30 dBs of range, which is fairly large considering the amplifier is not actually designed to be linear in any way. I would imagine that power output is fairly non-linear, or efficiency is fairly bad at low output powers. That's the RF output. I haven't taken this output filter apart. I know it's a low-pass filter and it's probably made on some sort of ceramic substrate, if you can see from the side here. I haven't measured it, but I know that it's a low-pass from the schematic, so it can be used for 70 centimeters as well. Okay, well, it's about 2 days later. What I've done in the meantime is I've modified the power supply, Corsair one, to give about 13 volts with load. So that's all good. I get a bit more output power now. I don't really need it, but it's nice to have the option. I just twisted some wires together here. There, I'm touching them. That's the keying and AF interface which heads over to the transmitter. I got the beefier wires on the transmitter with some strain relief here. Put the lid back on to reduce the amount of LO leakage. I did find I had to use separate transmit and receive frequencies because the local oscillator in the transmitter is always on, though it's obviously greatly attenuated. It does affect the performance quite a bit in terms of range when this thing is receiving the local oscillator from the transmitter. I had to do a fair amount of tuning here after doing the range testing. I also had to do a lot of antenna work because my antennas were awful. So what I found was that these cans here were very important to get the strongest LO signal. Otherwise the minimum signal level was greatly increased, or sensitivity was reduced. Tuning this had some effect, and there's also some tuning of a VCO tuning cap in there, which doesn't do a whole lot, but it sets the center frequency for the demodulator. So tuning all of those things made a fair difference to range. Additionally, you can't see it, but I've modified the bottom side of this antenna connector on the receiver, and I'm noticing I haven't remembered to put the screws back in, I think, since I did that. But this now has a 3.3 volt output DC bias, which heads over to the antenna over a piece of RG58. And I stuck a little 20 dB gain stage with a low noise amplifier that I already had built previously. That significantly increased the sensitivity of the system, and that was pretty poor to begin with. Cable losses were a factor. I had some bad antennas I thought were pretty good, but turns out they weren't. So now I'm using a collinear stack antenna with 8 elements, which has about 10 dBs of gain for receive signals. I can just show you the waveform of the receiver when I key it up there. There's a bit of BR. There's a slight problem with the AF interface to the modem. I disconnected all the filters and just made a gain stage with about 4x gain from the discriminator over to the modem there. One thing I hadn't mentioned before is I actually reverse engineered this pin header on the modem board to get the AF interface in a bit, make that a bit easier to use. That's a pin header intended for the ITRX analog signal inputs, but that actually works for interfacing a radio too, except for the keying interface, which I had to run over to the DIN connector. Yeah, as you can see, the squelch isn't set perfectly. It does occasionally blink. Obviously, adding the preamplifier, even with a tuned antenna, it's still a problem that sometimes there's a bit of interference, but the overall gain in sensitivity is worth it in this case. I might add a filter like this to the front end before the amplifier out at the antenna end, just to reduce the out-of-band emissions, but I am using a tuned antenna instead of the disc cone, which does help quite a lot. I also solved the problem with the transmitter. I don't want to take the lid off for this, so I'll just show you on the receiver. Basically, those cans there also exist on the transmitter, and when you power up the transmitter circuitry, it actually loads down the VCO because now there's current being pulled. So if these cans aren't perfectly tuned, they'll actually load down the VCO enough that it starts oscillating. Or rather, it starts oscillating because it's not particularly stable, but the fact that there's a disturbance being pushed into the VCO is a problem caused by loading, presumably the wrong input impedance at the on the doublers on the exciter board in the transmitter. So fixing that was it took a bit of thought to figure out that issue. Had to narrow down to eliminate power supply issues and other things which are usually the problem. And now we can actually key up the transmitter as well. It does key up, and if you look on the screen here, if it was shifting in frequency, you'd see that the signal would disappear when keying, but it doesn't. So yeah, I have to figure out this bit error issue. That's kind of annoying. It seems to happen mostly when I key up for a short while, so I think it's an issue with settling at the DC level side there. Range testing went reasonably well. It's not ideal. I think there's this AF issue. That's why I've decided to add a bit of gain to the signal stage. I'm hoping that might be the problem. But otherwise, I was able to get better range than my old VHF system with the current setup, which I'm pretty happy with. I'm not sure what output power I'm running at, but I don't think it's too high. And I'm getting a decent performance there. I can usually receive anywhere I can hear, and then there's a bit of margin for that. Cabling turned out to be a big issue. I had to initially had like RG174 cables and such. This RG58 is actually not particularly good either, as you probably know, but so I need to get some RG213 and also get rid of these stupid UHF connectors. They're not very good at all. Yeah, N connectors and RG213 for the antennas. That should be all good then. I also need to check that I can short circuit this output without the resistor on the bottom side of this board melting. That might be nice, since a lot of antennas have DC shorts normally, or at least just label the front here that it's 3.3 volts. Yeah, so that's all good. I don't think I wired up this button to do anything, but one thing I didn't show previously is when you change the frequency on the receiver, that actually lights up, and that's the PLL lock signal. So when that LED is lit up, that means it's not locked. You can see that the output basically locks in very quickly and nicely, unlike the transmitter, which is actually slightly unstable when it's cold. So there's a bit of work to be done, but once I get the Ethernet plugs for the back there, it should be coming along quite nicely. I'll be able to run it with the lids on and stuff. So yeah. Oh yeah, the 13 volt power supply. Turns out when you put a load on, the supply drops by quite a bit. But I was able to increase the output power by maybe a factor 2 or so by increasing the supply voltage by about 1.5 volts under load from 11.5-ish to 13. So I'm quite happy with the modded power supply. There it is.